Okay, kiddos, this is chapter 5, the atomic structure and periodic table chapter. In my opinion, this is the first time that you are really going to experience chemistry. This is the first real chapter, but a lot of these chapters, a lot of the concepts in this chapter you have seen in other biology classes and other physical science classes. So in class, I have you on a separate piece of paper draw what you think an atom looks like. If it has any parts, try to label them, draw to scale, and then this is the pretest. I have you guys write your name on it, and then I collect it, and then I give it back to you later on at the end of all these lessons so that you can see how much your understanding has changed. And hopefully we ended up learning something about our atomic structure. So let's begin. All right, so the first things first is the development of the idea of an atom and how it went from a philosophical idea to this theory that we end up using all the time. All right, so atoms, as we already described in previous chapters, are the smallest particle of an element that retains properties of that element. Okay, the word atoms comes from a Greek word atomos. Okay, and atomos, not atomos, atomos means indivisible, with liberty and justice for all. Okay, so indivisible, meaning that you can't break it up. And the reason why it's Greek is because of this fellow right here. This is Democritus. He was a Greek philosopher in the 4th century, so I think it was like year 340 something AD. And he first suggested that the idea of atoms existed. Basically, all these philosophers met around, whatever place they were at, and he said, if I take this piece of cheese and I divide it in half, and then divide that in half, and then that in half, and then that in half, and 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 in half, to this very teeny tiny little fundamental part, I will have an atom of cheese that will be indivisible. And he called them atoms. Okay, so obviously there aren't elements of cheese on the periodic table, although that would be delicious. Um, but that is the idea of what he came up with things like iron and copper and all these other kinds of things. So that was mainly left out there for hundreds of years until the 1700s when chemists were able to figure out things based on individual atoms. Okay, you should trust atoms. They really do make up everything because that is the building block to our entire world. All right, so in the 1700s, they determined that the average atomic mass of an atom is 10 to the negative 23rd grams, which is like inconceivably small. And the diameter is 1 times 10 to the negative 8th centimeters. And that's also really kind of hard to figure out. So that would be 100 million copper atoms in a row would be 1 centimeter, which is basically going to be the width of your pinky nail. And that's a lot, okay? And copper is a pretty big atom. Okay, 1 inch is equal to 2.54 centimeters. So a centimeter is really, really small. Okay, in class and linked in my website and in this Google slide is the cell scale and the size of the universe, which are two really cool websites where you can zoom in, and it starts with like a grain of sand or salt, I think it starts with, and then it goes into, your phospholipid bilayer, and then it starts talking about, individual cells, and then it starts going into atoms, and it's really cool to see how small things are. And that's where it starts taking you into 1 times 10 to the negative 12th, which is going to be your picometers. And then the other cool website is the size of the universe because it goes in both directions. So it starts with this grain of salt and it goes smaller all the way down to subatomic particles down to Planck and Planck's constant and string theory, which is like 10 to the negative 23rd, which is this kind of stuff. Oh, no. Planck is 10 to the negative 34th, my bad. And then it also gets bigger. So it starts going out to the size of things that you can see with the naked eye and out to the observable universe. So I would definitely click on those guys and play with them because it's kind of a bit of a mind melt getting all of that stuff into perspective. All right, so what changed? What changed Democritus's way of thinking to our current way of thinking? Believe it or not, it's the scale. Okay, that law of conservation of mass. Remember we talked about this? That mass cannot be created or destroyed. It's merely just transformed from one thing to another. A scale, the ability to weigh things, the quote unquote technology to house different kinds of experiments and gases and weigh A and B and C and see how they all interact. It's really quite remarkable that something as simple as a scale really led to the concept of an atom. Okay, so if you, according to the law of conservation of mass and matter, if you take atoms of element X, let's say that these weigh 8 grams, and you react them with atoms of element Y, and let's say that they weigh 4 grams, the resulting compound cannot be created or destroyed. So what does that equal? 8 plus 4? Yeah, it's going to equal 12 grams. And it's amazing that something as simple as that really led to, the birth of chemistry. Chemistry is a very relatively young science. Okay, it's really not going to be that old. Like biology and physics are very, very old since the dawn of time. But chemistry really is in the 1700s is when it all started. Okay, old school 1990s TV. This is my dad. Not really, but that was my dad. And then we had these big TVs, and then it got a little chubbier. But hey, there was a conservation of mass, right? As the TVs got smaller. So, who is credited with becoming the father of chemistry? So the father of chemistry is going to be John Dalton. Okay, so John Dalton right here, he's a British school teacher, and he came up with 5 postulates, 5 parts of describing atomic behavior. So he did all these different kinds of experiments, and he figured out that if we do have these subatomic particles, there has to be 5 different things that are met. So here we go. Number 1. All elements are composed of tiny, indivisible particles called atoms. So this was his homage to Democritus. And this was him saying, like, all right, I'm giving you a shout out because I know that you originally came up with this idea. So yeah, we're going to include you. Okay, you're the OG. All right, so number 2, atoms of the same element are identical. So that means if you are over here in Japan, and you are over here in Egypt, okay, you're going to experience the same elements in the same way. So copper over here is going to be like copper over here. And it's going to be different from aluminum the same way that it's different from aluminum over there. Obviously, that seems like an obvious statement. However, it's really kind of profound that you have to, put that out initially. All right, number 3. Atoms of different elements make up compounds in whole number ratios. Okay, so elements are going to be like letters of the alphabet. And our compounds are going to be like words. All right, so that's how they all fit together. So if you see something like H2O, what that is telling you is that you end up having a 2-to-1 ratio of your hydrogen to oxygen. That's an implied number 1 right there. Okay, C12H22O11, that's sucrose, that's your sugar. That's going to be a 12 to 22 to 11 ratio. Again, all whole numbers. You know what you're not going to see? You're not going to see this, H2.503 because if things are indivisible, you can't have half of a hydrogen and you can't have 3/4 of an oxygen. That's just not going to work. No way, no how. Okay, so number 4, chemical reactions are going to occur when atoms are separated, joined, or rearranged. So you can have things like H2 and O2 make H2O. You can have HCl break up into H2 and Cl2, or you can have something switch like Mg plus HCl is going to make MgCl2 plus H2. So like these guys just switch their locations. All right, they're not actually changing from one element into another. So you're not going to get any lead and then change it into gold just by, removing some protons or something like that, which obviously they can know about protons. So the gold rush and all those people that were tricked with fool's gold and promises of all kinds of riches, those poor people didn't know their chemistry. And then lastly, number 5, atoms cannot be subdivided. All right, so over here, Mr. Einstein, Professor Einstein, he cannot take his hammer and chisel and start to break apart and make these things into smaller pieces. Because it goes back to the whole cheese thing. You can't go and, make something smaller than the smallest piece of cheese. So obviously, we have some modifications and we have some updates, and the upcoming videos will talk about how his atomic theory is going to change over time with the development of technology and with our resources. So that is the atomic